Thank you, Chris. I've changed my title and increased the number of revolutions from 2 to 3, so my title now reads, From Eniac to Edvac, 3 Revolutions in Computers. I'd like to say at the outset that this is a draft written hurriedly in the week before I came. Some of the points, particularly the numerical estimates and dates, may be off. I'll read them without qualification and invite your corrections and suggestions for the final draft. There has been a long controversy over who invented the stored program computer. Unfortunately, this question is overly simplistic. The development of the stored program computer took place in many steps and involved many people. I will trace this development through its main stages, starting with the antecedents of the Eniac and ending with the first generation stored program computers, Edvac, Institute of Advanced Study, EDSAC, and UNIVAC 1. I shall refer to these computers collectively as the Edvac family. It is my theme that this period saw 3 important revolutions in computers. The first was the employment of vacuum tubes to make a fast, reliable, powerful, general-purpose computer. This development began with John Atanasoff's slow, special-purpose electronic computer. It culminated in Eniac, developed, designed, and built under the direction of John Markley and Press Eckert. Eniac was truly revolutionary. It was the first general-purpose electronic computer and computed 1,000 times faster than its electromechanical competitors. It inaugurated our modern computer age. The Edvac family of stored program computers embodied 2 more revolutions. A hardware revolution that made possible the electronic storage and electronic manipulation of programs, and an organizational revolution, the simple von Neumann computer organization and method of variable programming. In my discussion, I will ignore input-output equipment, for the hardware revolutions of Eniac and Edvac concerned the size, speed, and cost of internal components. The computing part of Eniac dominated its I/O equipment both in size and cost. Today, the situation is reversed. The logical equivalent of internal Eniac can be put on the end of your finger, and it costs much less than Eniac equivalent I/O. One aspect of the internal versus I/O contrast has not changed. Some of the older and more experienced engineers at the Moore School were skeptical about Eniac. 18,000 vacuum tubes? No one has ever operated a system of more than 100 tubes or so. At any moment, at least 1 tube will be inoperative, and that may spoil the answer. We responded with the opposite view. Our motto for the design of Edvac became a computer with no moving parts. Remember, in those days, most computers were bright, attractive young ladies operating desk calculators. We turned out to be right. The electromechanical I/O of Eniac and Edvac gave at least as much trouble as the electronics, and so it has remained to this day. I have distributed a diagram showing the main antecedents of Eniac and the Edvac family. The left half concerns hardware and arithmetic design. The right half covers machine organization and the method of variable programming. There is not time to cover all these antecedents in detail, so I will skim over the high points. The arithmetic design of Eniac was influenced mainly by 2 kinds of electromechanical calculators, desk machines and IBM punch card equipment. The toothed wheel and stepping switch became an electronic counter, and the triggered ratchet or relay a flip-flop. At a higher design level, the high-speed multiplier of the Eniac did fast multiplication by essentially the same method as the IBM 601 cross-footing multiplier. One of the designers of the IBM 601 wrote me a few years ago, "I didn't think that you were doing anything in Eniac but making vacuum tube versions of our machines." I am reminded of what Sir John Fleming, the inventor of the vacuum diode, said of Lee de Forest's invention of the triode. "That is no invention. All de Forest did was add a third wire to my valve." Adanasoff pioneered in using vacuum tubes for computing, but his vacuum tube switches were slow. Physicists used fairly fast electronic circuits for counting cosmic rays, but these did not need to be, and were not, very reliable. One of the first development tasks on the Eniac project was to design reliable counters that worked at 100,000 pulses per second. Eckert and Mauchly offered, and Army Ordnance wanted, a machine that could compute trajectories at least 10 times as fast as a differential analyzer, and at least 100 times as fast as a human computer with a desk calculator. This required a large machine. How much smaller it might have been with a better logical design is an interesting question. But in any case, it would have been at least 2 orders of magnitude larger than any known electronic system. How could such a large electronic system be made reliable? Eckert and Mauchly solved this problem by formulating and imposing rigid safety factors on all electronic designs, by employing a few basic circuit types, by mounting circuits on removable plug-ins whenever possible, and by incorporating diagnostic modes of operation in the design. I have time to mention only one more Eniac hardware constituent, the resistor matrix function table, invented independently by Jan Reichmann of RCA and Perry Crawford at MIT. It was a way of using linear resistors as switching devices in read-only memories. I have heard that when Jan Reichmann told von Neumann of his invention, Johnny replied, "That can't work, Jan. It's just one big short circuit." The resistor matrix used resistors where one would have liked to use diodes. So there were many current paths from each input to all outputs. But with careful design, the desired paths had much less resistance than the undesired paths, and output gates could safely sense the difference. By this method, the Eniac function table stored a total of nearly 4,000 decimal digits, as compared to a total of 200 decimal digits stored in the accumulators. The function entries were set with switches, but the readout was electronic. When Eniac computed a trajectory, the ballistic drag function was stored in one of these function tables. Without the resistor matrix, the values of the drag function would have to be brought in from the outside as needed, a much slower process. At its dedication, the Eniac computed a trajectory in 20 seconds, faster than the shell itself, which took 30 seconds to reach its target. In summary, many of the hardware and arithmetic designs of Eniac were high-speed vacuum tube adaptations of the technology of desk and IBM machines. The Eniac machine organization paralleled that of the differential analyzer. Adanasoff suggested a discrete electronic version of the differential analyzer. The Eckert and Mauchly 1943 proposal, on which Ordnance staked about $100,000 against the advice of the scientific elite of Washington and Cambridge, was titled Report on an Electronic Diff, spelled D-I-F-F, Analyzer, with a footnote explanation that diff could mean either differential or difference. Vannevar Bush's differential analyzer was a mechanical analog computer for solving differential equations. The Moore School had built one for itself and a similar one for Aberdeen Proving Ground. The differential analyzer was general purpose. It could solve a wide class of differential equations. It had three types of calculating units: integrators, gears as constant multipliers, and differential gears for addition and subtraction. These units were interconnected by rotating shafts. The whole system was driven by an independent variable shaft rotated with an electric motor. The integrator consisted of a metal wheel riding on a glass disc at a variable distance from the center of the disc. The wheel output was the integral of Fy dy. This integral quantity was transmitted to a shaft via a torque amplifier. Multiplication took two integrators and one differential gear. I'll show some slides. First slide, please. There's been some problem of identification. I believe this is the MIT differential analyzer. And these are the integrators along there, one in each box. Those are input-output tables, and I said I won't talk about input-output. These are the shafts which communicated between the integrators, and mixed among those shafts there are differential gears and gears which give factors of multiplication or division, which are constant. This, I believe, is again the output, the printer output. The next slide. This is, I believe, the Aberdeen differential analyzer with the integrators along the left, and here are the shafts. Here, I guess, is the printer. I'm not sure where the motor is that's driving the time shaft, and again, there are gears connected in there. To program the differential analyzer for a particular system of differential equations, the operator interconnected the calculating units, the integrators, and the gears by means of shafts in a pattern corresponding to the equations. Next slide, please. Here is a diagram from Douglas Hartree's book showing the program for the following equation, where x is the independent variable and y the dependent variable. The equation, you can kind of read it off down at the bottom, that is being solved by this setup is dy by dx equals a minus the integral of dy dx dy plus the integral of y cosine of x plus y dx. Note particularly the leftmost two integrators up here, which are interconnected to produce the sine and cosine of x plus y by solving the corresponding differential equation, d second w dx second equal minus w, where w is x plus y. And this illustrates the motor which is driving the independent variable shaft x. I'd like you to store this diagram in your memory for later comparison with Eniac programming diagrams. Next, I'll show you a figure from the 1943 Eckert-Markley Eniac proposal. Next slide, please. Oh, here it is. This figure shows how the proposed Eniac accumulators and multiplier, accumulator, multiplying unit, could be interconnected to solve the second-degree equation yielding a sine or cosine. If I had time, I could transform this diagram into one isomorphic with that of the two leftmost integrators of the previous diagram, which were also producing sine and cosine. The differential analyzer was programmed manually with a wrench in one hand and a gear in the other. Eniac programming was also manual, but it was more like wiring an IBM plug board. Here is the IBM 601 cross-footing multiplier mentioned earlier. Next slide, please. And here is its plug board. Next slide. Wired for the operation A times B plus C plus D. That's the cross-fitting operation. The brushes are connected to the multiplier and multiple can counters at number 1. There you see the number 1, number 1. And actually this diagram is overly simple with respect to reality because each of those lines there represents a set of 5 wires going from those 5 pinpoints to those 5 pinpoints. The brushes are connected to the multiplier and multiplican counters at 1. The numbers to be added, C and D, go into the partial product counters at 2. And there is a 1/2 entry to accomplished by wiring, a round-off. The stepwise multiplication results go into the left-hand and right-hand partial product counters at 3. Some controls are wired at 4, and the answer is connected to the punch at 5. In the differential analyzer, every shaft carried data. In Eniac, there were 2 kinds of cables: 11-wire cables for 10-digit signed numbers, single wires for control pulses. Manually operated switches determined what instruction a local control executed. Thus, the operation of programming Eniac had 2 parts. And there are some of the programmers here who can vouch for this. Cabling up data paths, and second, setting program control switches to enter instructions, and wiring up program controls to form sequences of instructions. By comparison, in the Edvac family, the former operation, that is the data paths, was eliminated by having fixed data connections, and the latter operation, setting up the program, was replaced by the stored program. I will illustrate these points with slides, and I'll just throw 3 slides of Eniac. Next slide, where you can see these trays which carried pulses both below the units and above the units. Are not so clear in this picture, will be later. Then these trays are connected together at the ends, and they're connected into the units proper by means of wires and cables. This is one of the storage function tables that could store 100 12-digit numbers or 206-digit signed numbers. Next slide. Everybody who shows Eniac slides shows slides with their own picture in it. This happens to be me sitting next to the multiplier. Here are the digit trays below, and there are the program trays above. Here are the faces into which you connect the plugs, the faces of the individual units, and on those faces, you can barely see it in this picture, there are the switches that are set. There should be another slide of Eniac. Did we miss it? Yeah. Well, that shows very well the digit trays down below, and there you can see the faces of the units that are programmed, and you can see people programming, one person giving instructions to the other, setting switches and plugs. 2 minor comparisons between the differential analyzer and Eniac are worth noting. The single independent variable shaft of the former, of the differential analyzer, became 10 cycling unit or clock wires in Eniac. Multiplication division by a constant gear ratio in the differential analyzer became a plug in the Eniac, in which wires were shifted to obtain a power of 10. I hold such a shifter in my hand, which would multiply by a power of 10. It's marked plus 1, and it does this just by moving the wires over in one position. Incidentally, all these things of Eniac were thrown out. All these plugs and cables were thrown out. A number of years back, an acquaintance of mine at Aberdeen happened to save that one and gave it to me. I show next how an Eniac program diagram looks. And ask you to compare it to the Hartree Differential Analyzer program stored in your memory. That's the layout of the Eniac. Let me just point that out. This shows all of the units so you can see a picture. They were positioned in U shape, initiating unit, cycling unit, or the basic clock, which produced 10 kinds of signals, the master programmer that John referred to, and here are function tables, 1, 2, 3, accumulators spread at both various places, a divider, square rooter, and a multiplier. So I want the next slide after that, which should be, I show next how an Eniac program diagram looks and ask you to compare it to the Hartree Differential Analyzer program stored in your memory. Now this is just a schematic program from a diagram, an article of mine written at the time, but you can see the accumulators connected here. You can see a representation of the digit outlets and inlets of the accumulators. You can see a representation of the program controls, and you can see the program control wires that are being connected here to solve a very simple differential equation, dy by dx equals y, with the digit trunks above and the program wires below. Now next I'll show you the actual program chart which was used for programming. I'm afraid at this distance you can't see much about it, but you can see representation of the number trunks, representation of program wires, and then the connections into the individual units, and those little boxes would contain a symbolism which would tell the operator how to set the switch in order to impart to the Eniac a particular instruction. Eniac was planned as a parallel machine, capable of doing many operations simultaneously. It was thus a multiprocessor. Not long ago, I was giving a lecture and wanted to display an Eniac program tray, which was 8 feet long, 1 foot wide, an inch thick, made of heavy metal. A computer science student was nearby, and I asked him to help me carry it to the lecture hall. He looked very uninterested, and I could see him thinking, that piece of junk? So I said, that's part of Eniac, the first general-purpose electronic computer. He remained unimpressed. Finally, I said, that's part of Eniac, the first multiprocessor. His face lighted up, and he rushed to help me. I think this illustrates John's point about how words come in and have meaning, and the concept was there all along, but now there's a new word. However, Eniac was not a modern multiprocessor. No Eniac unit could compute by itself, just as no unit of the differential analyzer could compute by itself. Addition in Eniac, for example, took 2 accumulators, one as transmitter, the other as receiver. A single full electronic arithmetic unit didn't come until Edvac. The 18,000 vacuum tube Eniac proved that electronic technology could be used to make fast, powerful, reliable, general-purpose computers. Its speed of computation was 3 orders of magnitude greater than the speed obtainable with electromechanical technology. But its organization and its mode of programming came from electromechanical computers, both analog and digital. Hence, the Eniac revolution was in calculating, not in programming. The programming revolution was inaugurated by the Edvac family. The Edvac family was developed in two distinct stages. First came the creation of what I will call the Edvac concept. It's indicated in your diagram, consisting of the Mercury delay line storage and von Neumann's machine organization based on it. The second stage was the development of the specific computers of the family, Edvac at the Moore School, EDSAC at Cambridge University, UNIVAC 1 by Eckert and Mauchly. The Institute for Advanced Study Machine carried the development one step further. The Mercury delay line storage was invented by Eckert and Mauchly. It was a virtual memory in which 1,000 pulses, or absences thereof, spaced 1 microsecond apart, cycled around. For most of this cycle, they were acoustic waves in a tube of mercury about 5 feet long. For the rest of the cycle, they were electrical pulses which were normally put back into the mercury tube, but they could be taken out and could be replaced. Piezoelectric crystals at each end of the tube of mercury converted electrical pulses to physical vibrations and back again. The Mercury delay line memory of Eckert and Mauchly was a beautiful invention. About 10 vacuum tubes or envelopes were needed to reshape and retime pulses and to switch pulse streams in and out of memory. Hence, 1,000 bits could be stored at the cost of about 10 vacuum tubes. In Eniac, electronic storage was by means of flip-flops and counters, costing about 1 envelope or double triode per bit. Thus, the new memory was better by a factor of 100 to 1. It was now possible to store program information as well as data electronically. Here are the Mercury delay line of Maurice Wilkes' Cambridge EDSAC, the first machine of the Edvac family to be operational. Next slide, please. The Mercury delay line storage derived from ultrasonic delay lines used for timing radar signals. To time a radar pulse out and back, one sent a pulse down a delay line and reflected it back. William Shockley built the first radar line at Bell Labs. Press Eckert developed the Mercury form at the Moore School for the MIT Radiation Laboratory. And Chris Brainerd mentioned earlier that work. The principle of a recycling electronic memory for computers was first employed by Atanasoff, who mounted electrical capacitors on a rotating drum. He restored the signals periodically, quote, jogging the memory, as he put it. But in comparison with the Mercury delay line, his cyclic memory was mechanical and it was slow. The Mercury delay line store led to von Neumann's computer organization and programming method. Von Neumann worked out the first logical design of a stored program computer in his 1945 draft Edvac report. Here is the cover of that report. Next slide, please. And here is the overall organization with which you are all very familiar, the Edvac organization. Next slide. Instructions as well as data were stored in the memory, mixed at the programmer's convenience. Instructions were executed by the control in sequence one at a time until a branch or jump was reached. The arithmetic unit added, subtracted, and multiplied, divided, shifted, and sensed. These operations were used both for data processing and for control. In control, the sensing was used for branching, and the arithmetic operations were used for indexing, the address part of an instruction being a computable number. In terms of organization and programming, the closest known antecedents to von Neumann's design were the Harvard Mark I and the Bell Labs general-purpose relay computers. In these machines, data were inputted from punched paper tape and processed in electromechanical arithmetic units. Instructions were coded and also stored on paper tape, but only those instructions actually being processed were stored internally. The Mercury delay line storage made it possible to store long programs in high-speed read-write electronic memory and to process these instructions electronically. Since the pulse rate of Edvac was 10 times that of Eniac, there was no longer the need for parallelism to gain speed. The guiding principle of Edvac design was one thing at a time, down to the last bit. This was modified in the IAS branch of the family by processing word bits in parallel. Also, the IAS machine used electrostatic memory tubes rather than delay lines. Here's the machine in von Neumann. The last slide, please. Got one. Let's see, we've got one page first. Let me make one last point about Edvac before concluding. This concerns the separation of logic and electronics. In designing Eniac, we necessarily mixed logic and electronics. A gate tube performed the logical operations of not and, but it could only drive so much capacitance in the allowed time before an amplifier was needed, and the amplifier was a logical not. Consequently, the logical design of the Eniac proceeded pari passu with the electronic design. In contrast, von Neumann worked out most of the abstract logical design of Edvac in his draft report. He did this by using idealized switches with delays derived from the logical neurons of Warren McCullough and Walter Pitts. This abstraction of logic from engineering enabled him to do the logic of Edvac without simultaneously doing the engineering, and thereby made it possible for him to essentially complete the design in one draft. We all knew his designs were realizable because he had worked out the building blocks with the group before he wrote the report. I remember well a meeting in the spring of 1945 at which we discussed serial adders. Press and John had designed several serial adders, the simplest of which took 10 tubes. Not knowing of these results, von Neumann announced cheerily that he could build an adder with 5 tubes. We all looked amazed, and Press said, "No, it takes at least 10 tubes." Johnny said, "I'll prove it to you," rushed to the board and drew his adder. "No," we said, "your first tube can't drive its load in 1 microsecond, so an inverter is needed, then another tube to restore the polarity." And so the argument went. Von Neumann was finally convinced, but he was not taken aback. "You are right," he said. "It takes 10 tubes to add, 5 tubes for logic and 5 tubes for electronics." As this story indicates, von Neumann's design presupposed not only the Mercury delay line, but considerable circuit development. Moreover, the second stage of Edvac development, designing the specific computers of the family, required further research work and inventiveness. There is not time to describe this here. I will end with a short summary. Eniac revolutionized calculating. It was a reliable, fast, general-purpose electronic computer, but its programming was electromechanical. The Edvac family of stored program computers revolutionized programming. The Eckert-Mauchly delay line memory made possible the electronic storage and manipulation of programs. Von Neumann designed the machine organization and method of programming. I thank you.
Our meeting is now open for questions.
Hamming from Bell Labs.
Oh,
I'd like to ask a question. I seem to remember have gone down to witness a Binac, yet I never heard a word about it. Can you tell me anything?
I'm sorry, I didn't get
John can answer that question. It's about the Binac.
Oh, the Binac.
The Binac was an interlude in one sense. It was a great practice ground in another sense. And all of these things can be explained if I say a little more. When we formed the Electronic Control Company, which later became Eckert-Mauchly Computer Corporation, we were expecting from the Bureau of Standards, who were holding monies from other government agencies, primarily, and first of all, the Department of Census, the Bureau of Census, rather, we were expecting contracts to build something which we at first had called Edvac 2. And then we decided that another name would be better and called it Univac. Now, while we were doing that, it became necessary, it turned out, to satisfy a lot of things, which John Curtis best knows, that we do these contracts for Univacs in two steps. First, by design, a design report, and then later they would see whether they wanted to give us a contract for actually building. Along came the Northrop Aviation Company, I guess it was, and said, look, we're interested in this kind of technology and we think we can use it. And in fact, we think you might be able to build a small enough computer so that it could fly in some little thing like an ICB or something, ICBM or something. They didn't say exactly what at that point, but it was supposed to be very light, small space, and eventually airborne. So he looked over that for a while and decided, yes, if they weren't too strict about how small the space and everything else, why, we could try at it. And they twisted our arm, and we took the contract. They twisted very little, actually, maybe it's a negative twist, because we were anxious to be doing something, and here we were waiting for a von Neumann committee to meet and say, should the Univac building go ahead? And that committee had to meet because the Bureau of Standards had divided the Univac contract into the study part and then the go-ahead part. So we ate. We actually had bread and butter and meat during that period when we were waiting for another contract to say go ahead, and what we built was a Binac. Now, if you don't know what a Binac is, why, we can say that it too was an Edvac-like machine, but in our caution, we built it in two halves. We had a left brain and a right brain, if you like. We had everything duplicated, including the checking circuits, which said, is the right part doing the same as the left part? And at something like 4 megacycles, I guess, rep rate, why, that thing, the right had to agree with the left, and the left had to agree with the right, including the right checking circuit and the left checking circuit cross-connected. And if anything happened, why, in one quarter of a microsecond or so, everything came to a halt, and we knew how to investigate, find out what was wrong. It was a great proving ground for techniques, and it convinced us, among other things, that we'd do better if we halved the rep rate when we came to building a Univac.
The gentleman over here in a lavender shirt.
Mike Williams from the University of Calgary in Canada. Hearing all about the Mercury delay line storage reminded me that I've been trying to trace down the origin of a statement for the number of years, and I've heard it attributed to von Neumann and to Turing and to Stanley Gill and even this morning to Maurice Wilkes. And that was that due to the heat problems with Mercury, an alternate substitute was being sought. And somebody, and I'd like to know who, suggested that Booth's London Dry Gin had the ideal thermal properties. And I was wondering if anybody here can tell me who's the originator of that story.
If there's someone on the audience, answer, otherwise.
Wilkinson of MPL. I think there's no doubt that it was Turing's suggestion. I heard him say it, and he mentioned it many times when he was at MPL.
William Cleaver. I want to address my question to Dr. Burks. You made reference to the Atanasov device, and according to Dr. Atanasov, his device had neither an input nor an output. It did not divide nor multiply. It could only do a single operation before you had to re-enter the information. It was not programmable, and he never got a tube flip-flop to work. And I'm curious if you can give us some insight as to what his contribution was.
Well, I described his machine as a special purpose machine. It was designed to solve simultaneous equations by the method of repeated subtraction. It had the memory for these equations. He designed prototype arithmetic units and reported that they did work, and he designed the memory and reported that it did work. He certainly didn't complete the control or go very far in the control. I just don't remember what he did in the direction of control. If you read his report in the Randall volume, he has the principles of switching, and he designed adding circuits that could add and subtract. And of course, for his particular special purpose problem, he wasn't using multiplication.
My name is Cuthbert Hurd. Arthur, where does the SSEC and where does the whirlwind sit on your diagram?
Well, I was concentrating on the Eniac and the Edvac and trying to trace some of the antecedents to these machines. I wasn't going to follow any semi-parallel lines or any subsequent developments. I do have, of course, these machines, the Institute for Advanced Study machine, then the Edvac, Univac, EDSAC. I've indicated the IES machine as somewhat different because it used the memory originally planned. It was to be this electron memory that Jan Reichmann was working on at RCA, and when it was actually built, it was the Williams tube memory. So it used a different form of memory, electrostatic memory. And at the same time, though not necessarily connected with this at all, of course, it processed the bits of a word in parallel, whereas the Edvac concept had the bits of a word processed in series. So I really wasn't trying to address myself to those questions, Cuthbert.
Bob Beamer, Honeywell, because of the excuse me.
Come on, you in a second.
Oh, all right. Don Knuth from Stanford. I've been wondering for some time whether these McCulloch-Pitts type diagrams that von Neumann had in that 1945 report were really of use for engineers, or whether they were mostly of interest to mathematicians.
Well, maybe the best way to answer that is to refer to that story that I told about 5 tubes for logic and 5 tubes for engineering. Obviously, they were idealizations, and I think it a fair statement that at the beginning, Johnny didn't fully appreciate the extent to which they were idealizations, but after discussions of the sort I referred to there, he definitely did understand that they were idealizations. They nevertheless gave a logical notation for switching plus delay, which enabled him to work out this design. So I would say that in terms of his achieving this design in a relatively short period, they played a very essential role. Let me emphasize that the part that I didn't talk about, the development later on, which contained all the engineering, was of course terribly important. And I did use the word inventiveness and so forth in connection with that. Having this design didn't mean that the job was done by any means, and that, as the time is indicated here, I believe that the government attorneys in 1947 decreed that von Neumann's 1945 draft Edvac report was a publication. It had been distributed to a certain degree, and since it had come prior than 1 year to that time, that it was a statutory bar to patenting the concepts of the Edvac. That seems to me incorrect, because there were very few people who could take that design as von Neumann had developed it and converted it into a computer.
Before we go to another person in the audience, let me make a remark. That report of von Neumann's first place should never have been let out because it was supposed to be classified at the time, didn't go through proper channels and didn't come up to me. In the second place, von Neumann, to a certain extent, disowned it, remember, because he pointed out that he had no credits in there. He had talked a great deal with many people, and he had read practically all our reports. And he was up to date because of this, and of course added a great deal of his own, but it wasn't all his by any means. So that all in all, that report should be handled rather gently. Art, we got another question over here.
I'd like to just add one thing to that, because I think it is important that the report was reproduced without his knowledge, and kind of by chance. One of the faculty had a new secretary, and she didn't have anything to do, and they asked Herman, did he have anything to do? Yes, she could type this up.
Following recovery and restart, I'm Bob Beamer from Honeywell. And the context of my question demands that I also remind you that I was at UNIVAC a little decade or so ago as charge of programming. And I recall being in a staff meeting sitting next to Press Eckert when it was discussed the formation of the Illinois Corporation for the purpose of pursuing certain patents. Now, I can't remember exactly how that all went, but what I'm wondering is, what was the patent chain between Moore School and the Army, which may well have owned some, and Eckert and Mauchly and their individual things? And how did that come to...
The Moore School and the Army was that the contract very specifically said that either the Moore School was to take out a patent or the Army was to take out a patent. But if the Army did, it was to protect itself and was willing to designate others, the inventors supposedly, as the recipients of the, you might say, as long as the government got a license, it didn't care. This was in the contract that we had to follow. And when Paul Gillen of BRL came up one day and said let's not get into any position in which someone else picks up all these reports pretty soon and starts patenting things. The patent question arose, and that was a great, well, the only expression for it is it was a great bundle of worms. Bundle, I said, not even contained in, come on.
William Cleaver again. I'd like to correct one thing that Dr. Burks said with respect to von Neumann's report being considered for a patent. It was submitted to the Army for a patent disclosure, submitted particularly to Joe Church. And it was decided at that time that there was an insufficient disclosure with respect to hardware. That's the reason it was not filed.
I'm referring to a different statement, a statement made by government attorneys at a meeting in 1947, in which the statement was made that taking out a patent on Edvac would be barred in the eyes of these attorneys because of prior publication.
See, we have one over here. Yes.
I'm Louis Fine of California. I'd like to address a question to Dr. Burks. Between 1948 and 1951, there was a digital computer built called the Edvac. It was a Mercury delay line, 4 megacycle rep rate machine with a fully buffered plastic-based magnetic tape external memory. Happened also to be Freon cooled. I wondered if you would include that in your Edvac family.
Yeah, it's really a question of definition. There are lots of other machines, and we'll hear about them, SEACs and so forth, that go back to this idea, and perhaps it's arbitrary just to where to draw the line. The Moore School group that worked on the original Edvac concept did go different places, and some of us went to the IAS and worked on that machine. Some stayed at the Moore School or were replaced by others and built the Edvac, and then John and Press went and built UNIVAC 1. Wilkes, as I remember, came to the Moore School in the summer of '46 and learned about this and went on to that, and that's where I drew the line. But you're right, there are lots of machines that were based on this principle. Indeed, there was a MIDAC at Michigan based on this principle. I was not trying to include them all, but those that arose most directly from the people involved.
We have time for only one more question. Please.
Randall, Newcastle upon Tyne. This is not a question, rather a comment. as many of you will know, a tremendous amount of documentary material about Eniac and Edvac and other things was brought together in connection with patent litigation, the suit between Honeywell and Univac. I have been able to obtain microfiche copies of the entirety of the transcripts of the trial, which were, let me guess, as something like 20,000 pages, and also of the huge mass of pieces of evidence that were collected by Honeywell and Univac. I've described this material in a brief appendix to the supplementary bibliography that I've prepared, and I can now tell you that this material is also available from Mr. Halliday, one of the patent attorneys, for purposes of historical research. It is a quite unparalleled amount of material, even if one might have varying opinions as to the outcome of the trial itself.
One unparalleled amount. We in the Moore School have the Sperry-Rand complete files, set of files, 15 or so? Yes, filing cabinets. 21 filing cabinets filled with the entire Sperry-Rand side of the case. We've been after Honeywell to see if we can get the same thing. Of course, the court record, we can get it any time.
Let me explain it. That isn't quite right. What you have at the Moore School is the same thing that he has in microfiche. You have all of the exhibits that were put into the court, a complete copy of the transcripts and depositions, as well as an index so that historians can find their way around. It isn't Sperry-Rand side. It's exactly the same material.
People, our time is passed up. I think we should adjourn.